Well, since this section is all about taking derivatives of inverse functions, it probably would behoove us to just take a quick review and a reminder what an inverse function is. So um, first off, if y is f of x, and if it has an inverse, typically we would denote its inverse by x equals f inverse of y. And notice that we are, kind of a double using notation here. This -1 does not mean flip this. This does not mean the reciprocal. If I wanted to write the reciprocal, I would write f of y, and then I would raise the whole thing to the -1. That would be equal to 1 over f of y. So common mistake in notation, by the -1 being right there attached to the f and not on the outside, that this is talking about the inverse function. And what's true about the inverse function is that y, what's true about the inverse function is that x will be equal to f inverse of f of x. And similarly, y will be equal to f inverse of y. Right? So as functions, you can think that they undo each other. We can also visualize this graphically. So let's take a function, let's just say y equals x squared, where x is greater than 0. Then we know its inverse function is x equals y to the 1/2. Notice I had to make x be positive, otherwise this function doesn't truly have an inverse everywhere, but by restricting the domain, we do get an inverse function. And what do these graphs look like? Well, if I look at y equals x squared, so its graph would just be on the right-hand side, and it would be the parabola, y equals x squared. Now, on the other hand, if I graph, and notice this is the x-axis, so this will be very important. This is the x-axis, this is the y-axis. Now, when I flip it, I've now made y my dependent variable, and my y independent variable, and x is the dependent variable. So it would be y here and x here. And its graph looks, the square root graph is what that is, and it looks something like that. Now, my drawing isn't perfect here, but hopefully you can see the similarity that going from y equals x squared to x equals y to the square root of y, or x equals the square root of y, really all we've done is we've flipped this whole world along the diagonal. We've really just flipped it along there, right? So that the x goes up here, and the y-axis just comes around down here. And by flipping it, if you can kind of picture rotating about that, then this graph just does that rotation and is transformed over there. And so another way we could say that if we've got, and this is not special about invert or about this function or anything, any function, we look at its inverse, will just look like if I flip it, then their graphs are identical. And why should that be true? Well, thinking about how the inverse function, how functions work, this says if I start at some value a, then I go up here and would end up at this value a squared. Well, the inverse says, well, start at a squared and go into my function, and I come back at the value a. So we're, again, this kind of undoing makes their graphs, if we flip it around, their graphs are identical. Or back to this idea that it undoes the function, that x, if I apply f inverse to f, I get back to where I started. Whereas if I apply f to inverse, I get back to where I started. Okay. If you need more review on inverses, I recommend maybe searching Khan Academy or other YouTube sources for just more information generally about inverses. So now we're going to investigate taking the derivative of an inverse function. So I'm going to look at some examples where we take a look at a function for which we know what its inverse is and compute the derivatives of both compute the derivative of both and see what kind of relationship we have. So the first function I'll look at is a nice linear one, y equals ax plus b. If I solve for x here, its inverse, x, is equal to 1 over a times y minus b. So differential here, dy is equal to d of ax plus b. And differential distributes across. They'll pass past that. The derivative of b is 0. So in the end, I get that this is a dx, or that dy dx is simply a. Over here, if I take dx, this is the differential of 1 over a times y minus b. Similarly, the differential passes past the constant. I'll multiply or take the differential of y, differential of b, which of course is 0, and I get that this is simply 1 over a dy. So then that dx dy is 1 over a. Now, this we'll find is not a coincidence that I've got an a here and it popped up in it's the reciprocal here, right? It popped up in the denominator. So I could rewrite this that dx dy is the same as 1 over dy dx. So let's take a look at another one. So how about y is equal to x to the minus 1. So then x would be the inverse, would just be y to the minus 1. Then I'm going to do this real quick. This is just a simple power rule, right? And my power is -1, so the derivative of this function, the coefficient or the exponent comes down, becomes my coefficient, and I'll subtract 1. So dy dx is just negative x to the minus 2. Similarly over here, all I've done is switch the variables. So same power rule, dx dy is equal to negative y to the minus 2. Now, we know something about y, so I can, right, unlike the original one, we could see right away that the relationship, these have two different variables, but I know that y is equal to x to the minus 1. So I could replace that here. And so this is equal to negative. Now y is equal to x to the negative 1, so I can put this in for y. Still being raised to the minus 2 power. And this is equal to negative x squared. Now we can see much more clearly that, again, we've got this reciprocal relationship. This was x to the negative 2, which is right, negative 1 over x squared. And if I take its reciprocal, I get exactly this value. So I note that dy dx is the same as 1 over dy dx. It took a little bit more work to see that, but in both cases, dy dx is the same as 1 over dy dx. Dy dx is the same as 1 over dy dx.